Hello and welcome to Quizard Corporation's artificial blood vessel design presentation. I'm Reagan Terpstra. This will be for the benchmark presentation for ESG 455. So now the background of this presentation is focusing on bypass surgery that is needed when a blood vessel is blocked up. Now, normally when this happens, a second vessel is taken from another part of the body and it is then grafted in to both ends of the blockage so the blood can travel around the blockage and allowing blood to travel and continue to provide its important functions. But the only issue with that is that a vessel still needs to be removed from another part of the body. Artificial blood vessels will help remove that need to remove another blood vessel and allow blood to be carried back to that part of the body as well. Now, artificial blood vessels have about three main components needed to develop: a structural scaffold, vascular cells, and an environment where they can grow. Now, focus of this study is to determine the best material to be used for the scaffold structure in these vessels, as that's what really helps give it the support it needs to develop and become an effective vessel. Now, scaffolding structure consists of either a biodegradable polymer or collagen, according to Kakissis and others back in 2005. Collagen struggled with mechanical strength unless specific care was applied to the direction and orientation that the cells grew. And it is expected that the support sleeve will degrade. As it degrades, the cell layer will strengthen and be able to bear the load on its own. So it has a good balance of biodegradability and staying there long enough for the cells to develop. Now, on the polymer end, the most common type used is polyglycolic acid, or PGA, as it possesses high porosity, which allows nutrients to pass through easily, as well as the ability to be easily shaped. But it still struggles to uphold to systemic pressures and will only last 6 to 8 weeks because it's so biodegradable, which is really helpful in the end, because we don't want having random polymers in one's blood vessel, but it's still has that issue of not being structurally supportive when it needs to be. Now, to improve this ability, a copolymer is added to help lend physical characteristics that would benefit the development of the structure. So in this simulation, the goal is to determine a material that will be able to withstand the pressures while also being biodegradable and easy to work with to use as a copolymer. The simulation will represent a blood vessel in the body with different materials used. The vessel that we're trying to simulate will be a brachial artery, which provides oxygenated blood to all parts of the body. It's so super important. And this will have a 0.2 centimeter inner radius with 1 millimeter thickness in the simulation. That will be consistent across all simulation models. The only difference will be the length. For this experiment, the flow rate will be taken to be 5 times the normal blood flow rate of 5 liters per minute, and that comes from Harvard's BioNumber system. The simulations will run 3 times for each material, with the length changing across each runs, as mentioned earlier, from 1 millimeter to 10 millimeters to 100 millimeters, and at that flow rate of 25 liters per minute. The 3 materials that will be used in simulation are PHA, PLLA, and PET. I'll let you read out those long names yourselves if you want. These are selected as they're biodegradable polymers, and they could provide great support to the PGA. So here we have the model drawings for these parts. As you can see, on the far left is the 1 millimeter, the middle is the 10 millimeter, and the far right is 100 millimeter. They're all the same cross area for the surface there. The only difference is the length. So here again is the model drawing for the 1 millimeter, the 10 millimeter as well, and the 100 millimeter length model drawing. So these will be used for all 3 materials. They will all 3 materials will use all 3 of these model designs. So here we have the simulation results for the PHA. We'll get into the exact numbers later, but if you look on each of these drawings, you'll see on the 1 millimeter that it doesn't really experience that strong of intensive a pressure. It only has, if you look at the scaling on the side, the red is a more extreme pressures, blue is a lighter pressure. So the 1 millimeter model on the left doesn't really experience too much pressure. It increases with the 10 millimeter on the bottom right, and on the top right, you really see that the 100 millimeter really experiences a lot of pressure as it goes along, which makes sense as you have a longer area and intense flow rate flowing through it, the pressure is gonna increase as it flows. And we have similar results for the PLLA as well. If you compare the two, it feels like there's more. It kind of withstands a little bit better, but just as good as very similar to PHA. The PET, it kind of struggles a little bit more. If you look in the bottom right, the 1 millimeter, we see some yellow there, which the other two didn't really ever have. So 10 millimeter gets some red into it, and the bottom left there is the 100 millimeter, and it's just very high values that are outputted there. So now we can see these values here. The PHA, PLLA, and the PET all have pretty similar values, as you can see. They all have their maximum right around 7 or 8. PET actually experiences less pressure than PLLA and PHA initially, and they all have. But then, as it increases by a factor of 10 to that 10 millimeter, the difference starts to grow there a little bit. The PLLA, PHA are very similar across the board. 60 millimeters there, 60.8, nearly identical. And then PET really it jumps. It's pretty still right there with them, but it's jumped a bit to 67.8 megapascals. Now the 100 millimeter model is where it really gets interesting. So the PHA, PLLA still very similar, 91.1, 91.7, nearly identical. PET had a maximum pressure of 118 megapascals, so a good deal higher there, nearly 30 megapascal jump from the difference there. So that's something to notice there. Now looking at the cost, because that's another factor of this decision point, because it doesn't make sense ultimately if this is if very costly and expensive. So the cost per mass or per kilogram of PHA is 2.4 to 5.5 US dollars. This is a wide range there, so we're averaging that to 3.95 for our calculations here. PLLA 2.98 US dollars per kilogram, and not even a dollar for PET at $0.87 per kilogram. So that's very inefficient, which is nice to look at. Now our masses are pretty much the same, all less than a milligram for all of these models, so they're very small individually, which ends up making them being very cost effective and inexpensive, with PET easily being the least expensive of all of these, and PHA being the most expensive, just where we picked our average to be. But different masses are important to observe as well. And PLLA is also just nearly as expensive as PHA in the end. So then looking at what we recommend from these results, none of these vessels failed in simulation, which is great, so they should be able to withstand all of these pressures. And the pressure they experienced was much larger than the pressure that a normal vessel should experience, which ranges from about 14 kilopascals to 15 or 16 kilopascals. They all exceeded that value. PHA and PLLA seem to handle that better, with the pressure the pressures they experience being not as great. So that puts those ahead of PET. Now looking back at the expensive side of things, PHA has a lower starting price, but can jump up to nearly double the price of PLLA. Now the values that we used earlier were calculated from the average, so it can be double that price at some point if you never know what could happen. So taking account to both of these factors, how PLLA functioned just as well as PHA, but at a lower price point, we had to go ahead and recommend that for this artificial blood vessel design. I thank you and have a good day.